this is a induction proof. And the statement I want to prove is about series. 5 plus 9 plus 13 plus 4n plus 1 is equal to n times 2n plus 3. We know the general idea of induction. We have to show the base case. The base case is show true for n is equal to 1, and we can do that. And then we have to show the inductive or the successor property, inductive case or inductive property if we want. And that would be assuming true, if this happened to be true for a particular integer, n is equal to k, then it necessarily has to be true. Right? We have to show true for the successor. And the successor of k is k plus 1. Okay, so that's what we have to do. Now, to outline this proof, again, I'm thinking writing an essay. This stuff is just to show that a sub 1 is equal to s sub 1, and that's usually pretty easy to do. For this series, you would put 1 right there. So let's see, we have 4 times 1 plus 1, and that's supposed to be putting 1 right in here, right? Putting 1 there. So that would be 1 times 2 times 1 plus 3. And this better be true. This will work. You can check that out. Okay, the successor property is if we were to add the next term to the k partial sum, and we did this on our quiz, we're supposed to get the k plus first partial sum. That's what we're supposed to get. And again, it's not hard to check. This is sort of like scratch work at this stage. A sub k plus 1 is going to be 4 times k plus 1 plus 1. The kth partial sum is k times 2k plus 3. Somehow we would have to show this is equal to the k plus first partial sum, which is k plus 1 times 2 times k plus 1 plus 3. Now, if the statement is valid, this will be true. Just doing some scratch work to see where we might head with this. This is k plus 1, and this is 2k plus 2 plus 3, or k plus 1, 2k plus 5, or if you want 2k squared plus 5k plus 2k plus 5, or if you want 2k squared plus 7k plus 5, and this should be the same thing. Let's see, 4k plus 4 plus 1 plus 2k squared plus 3k, and if we just rearrange, we have 2k squared, there is a 3 and a 4k, so that's 7k, and we have 4 plus 1, which is 5. So they do match up. Now, all that's sort of like preliminary scratch work. What we want to do is do a very nice proof, a very nice proof. So I've got this now as a Word document on your class page. Here's the Word document, and let's take a look-see at this and see how it falls out. This is the statement we're trying to prove, and we're trying to prove it true for all natural numbers. So the first step, and you should write, you don't have to type this up, but you should write, the statement is true for the base case. And if you want us to be specific, that's when n is equal to 1. So in here we put a 1, there we put a 1, there we put a 1, that gives us this, right? And then you just simplify, double check, make sure that's good. Okay, so the base case is true. It is true when n is equal to 1. Okay, the second thing, the inductive step, is this. The successor property has to hold. So we assume the statement is true for an arbitrary number k, and that's this step here. Let's see the assumption. What I'm going to do is I'm going to rewrite this over again, this original statement, but I'm going to replace the letter n with k, there, and there, and there. So, and if you just note, this is exactly the same as the box up there, except everywhere there's an n, I put a k. So that's easy. And then somehow from there, we have to get all the way down to k plus 1. And this I'm going to call the goal, if nothing else, the goal. Okay, so the goal would be to take this original statement again, and we would have to show that it's true for k plus 1. So what I would be doing is right there I'd put a k plus 1, there I'd put a k plus 1, and there I'd put a k plus 1. And that's this line. So if you look at this carefully, you should see that here the n was replaced with k plus 1, here the n was replaced with k plus 1, and likewise here. That's our goal. Okay, and that is going to be this k plus 1 partial sum on the right with all of the terms that are added on the left. Now, how do we get from here to there? That's the task. It has to be strictly logic. So the first thing we do is we add the same thing to both sides. And for all series proofs, the secret to these is you simply add the successor. This term in the brackets is what comes after 4k plus 1. So after 4 times k plus 1 comes 4 times k plus 1 plus 1. This is the successor. And we're going to add that to both sides of the assumption. Okay, so this is still here. And I've just added the successor to both sides. And the reason I can do that is because of the addition property of equality. And now if you just note on the right side here, this is of this form. This is a sub k plus 1. This is s sub k. We're adding them up. And somehow we got to get down to this. And we already know it works. So we did the scratch work. But what I'm going to do is I'm just going to write a series of equations. So let me scroll down here just a bit. Okay, so this left side right here is this. It's exactly that. And if you could look at those two and be assured that those two are the same, okay, that's good. And then this just stays the same all the way. I really don't mess with the left side at all. The left side is perfect. Once I've added the successor, the left side is exactly what I need. So all I really have to do is play with this right side. And, you know, I've written down what's going on here. I know it will work out. This is my s sub k plus 1. If I just sort of work backwards a little bit, you can see I multiply through by the 2k plus 2, and that's the same as 2k plus 5. The k plus 1, if you multiply these out, right, that's the 2k squared plus 7k plus 5. And in fact, this, if we're working from this line right here, right down one, you can see we have 4k plus 4, that's this, plus 1, and then this is 2k squared plus 3k. So all the pieces are there. I just sort of clean them up, write them down in a nice logical way. You really don't have to write down the reasons on the right-hand side. And then at the end, and then, by the way, this is just sort of a side note, marginal note, if you will. And then at the end, write your conclusion step. Therefore, by mathematical induction property, this statement is true for all natural numbers, QED, that which was to be demonstrated. And there's a clean proof now. Look at these on your class page. We're going to practice these on Friday. I'll go and put together another 6 or 7 of these series proofs, and we'll do them tomorrow for homework. Okay? Thank you.